new particles are produced, and energy. It is the emission of the small particles called neutrons which generally provide the measure of successful fusion. The detectors to pick up the neutrons form part of the intricate three-dimensional jigsaw that makes up the jet experiment. But there is another challenge. The other product of the fusion reactions is hot helium ions. These are important because they sustain the plasma at an operating temperature by passing on their energy in collisions. However, when the helium ions cool down, they must be removed because they start to inhibit the fusion process. Removing the exhaust is one of the major challenges in sustaining the plasma. To achieve this, a device called a diverter is being installed at the base of the torus to trap the exhaust particles. Different designs are being tried out to see which proves the most efficient in sustaining the fusion process.
Move the boom to 17 OW, first rest point.
Once tritium is used as a fuel, the inside of the torus becomes too radioactive for people to work in comfortably. So a remote handling operation has been devised to implement changes to the diverter and cope with all the maintenance and upgrading activities in a fusion experiment. The centrepiece is a boom designed to reach all parts of the torus interior with its own cameras and lights. Attached to it is what's called a mascot with arms to carry out the detailed manipulations. There is also a virtual reality computer system designed to help the operator. This is state-of-the-art technology, a unique mix of computerized and human control pioneered by jet engineers. To simulate conditions inside the torus, an exact replica has been built with similar lighting and access. Tests here could avert costly errors in the real operation.
It has actually been very, very useful from a test point of view. And in fact,
while the remote handling system was being proven to install the new diverter, the teams of physicists were honing their detectors to pick up just the signals required. In the roof above the torus, the laser system was nearing completion, ready to probe the plasma temperature and position. By mid-1996, the trial of JET's new design was underway.
All ready, beams ready.
Each plasma lasts for less than a minute. The leaders of each session must adjust the magnetic fields and the injection of new plasma in the search for improvement. It's a trip into the unknown.
So now we're in the last 30 seconds of countdown. Gosh, that's quite a pulse, isn't it?
The results of every run are analysed and stored. Each team looks for clues in its own apparatus as to how the plasma is behaving with the new diverter.
Which is the bigger anyway? The 1 to 10 is larger, horizontal, so that's the way around it was.
I think the laser energy is down a bit, and I don't know whether that... Do you think that's straight line?
Yeah.
In the middle?
Yeah.
In our old familiar 3 metre straight line?
Yeah. We can signal there.
As the world's fusion scientists meet, the spotlight falls on the JET experiment. Plans for the world machine will be influenced by news of developments from JET. As the researchers ponder the latest results, a key question lies in the background. Why fusion is so important is that it can offer future generations an energy option which they may well need with all the uncertainties surrounding present fuels. If the world waits for a major crisis in conventional sources of energy, the time to call on fusion energy may be too late. It is a subject which brings continents together in cooperation and competition.
It's a the question is what happens in these 100 microseconds.
Which concerns nitrogen-related diverters that were quite frequently established at jets.
We see this deposit, which is 50% of deuterium in carbon, but I mean, what you don't know is actually in the machine at the end of the pulse.
A reminder of the tiny quantities of fuel needed for fusion power came as samples were unloaded in preparation for the big run. This canister contains just a few grams of tritium. In a real power station, just 1 gram of deuterium and tritium as fuel would replace 10 million grams of coal or oil. Also, the daily waste from such a 1,000 megawatt plant would be just 2 kilograms of helium for a fusion plant, compared to some 30 million kilograms of carbon dioxide, sulfur dioxide and other wastes from a fossil fuel plant. However, managing the fuel for a fusion plant requires special skills. A new facility has been built at JET to purify and recycle the fuel. This plant ensures that one of the hydrogen isotopes, tritium, is both recycled and kept isolated because it is radioactive. Safety is one of the foremost concerns in all developments towards fusion power, as it must be for any form of energy provision.
How safe is JET?
JET is very safe. It is not like a fission reactor. The amount of fuel in a fusion system is very small at any moment and consequently could only burn for less than a minute. The power in a fusion plasma is self-limiting and there is no chance of an uncontrolled runaway.
So there is no possibility of a Chernobyl-type disaster. Nurturing the vision of a clean, safe and efficient fusion power station requires bringing together both scientific and political skills in today's world.
Since I'm particularly interested in the diverter work...
The director of JET leads the scientific effort, but must also work directly with the European political infrastructure that underpins the project. In many ways, JET can be seen as a symbol of how the new Europe is working. The Commission in Brussels steers a fusion effort which includes the research in member states and JET, which spearheads the programme. The Council of Ministers and the European Parliament see that the political aims of Europe's energy strategy are met and approve the funds. It's Europe working at several levels: science and engineering, industry, European institutions and politics. And JET's latest experiment with tritium and deuterium as fuel has once more put Europe at centre stage. As the power is increased, JET scientists and engineers wait for the signs that the plasma is producing a new record in controlled fusion energy. This is the first time a pulse of more than 12 megawatts of fusion power has been achieved in a controlled fusion experiment. While a host of riddles still remain in scaling up the fusion process, this represents an important proof of some of the key technologies needed on the path to practical fusion energy. It is a reflection of the success of this European collaboration that a strong position has now been achieved by Europe as it prepares for the proposed world project called ITER. However history comes to place the JET experiment, one thing is sure: without such steps into the unknown, humanity may never have a chance to benefit from a potentially limitless fuel, a fuel perhaps cast to the needs of a new millennium.